Okay, so another day of logarithms. We're going to do logarithms today, tomorrow, Monday, Tuesday, group quiz, review, test. So lots of practice with logarithms. What are logarithms? Logarithms are exponents. You can write it like this. Log base b to a number is equal to an exponent. Logs are equal to exponents. Logs are exponents. Okay? This is how we find these. When we're trying to solve for an exponent, we take the inverse, which is a log, to find the exponent. That's what we use them for. That's what we're going to do today. Alrighty. So recall. So an exponential function with a base 2 looks like this. Its inverse function looks like this, and we would say it's log base what? 2. Right? And the x means log base 2. What about this one? E to the x. Well, I've got a question for you. Where are we crossing right here? At 1. Where are we crossing at 1? Where? Do they know? 2.71 actually. 2.711828, I believe. I don't like to say 2.72 because 2.72 is the limit. It can never hit 2.72, so why would I call it something like that? Does that make sense? So I call it 2.71. Even though it's 2.718, it's closer to 2.72, but if it'll never be it, because I'm never going to be a millionaire, okay? I'm going to be a millionaire. Actually happens, right? Okay, so this one, the important part to look at this one is that if my exponential function is with me, then my logarithm is with base t. Thank you. And then we just remember this one has a special, its own name. Ln. Natural log. I don't know why we don't call it log natural. Then what do they call it now? It's actually a really cool lesson, guys, because what we're going to do today, remember when we first started solving exponential functions? And, guys, I'm having a whole conversation over here. Remember when we first started solving exponential functions, we were actually solving for, we used Desmos. We wanted to know, like, after how long a baseball would be worth, I forget, $50 or something. We had to use Desmos because we couldn't solve for those exponents. Well, now we have a way of solving for those exponents. So we're going to go back to that worksheet, and we're going to solve it using logarithms. Okay? That's kind of what we're going to do today. All right, so compare and contrast. So this is what we used to do. Can you solve this without even using algebra? Most of you should be able to tell me that x is 3, because you know that 2 to the 3rd power equals 8. Well, the way that we did this algebraically was we said we needed to find common bases. So I had 2 to the x equals 2 to the 3rd. Now I have common bases. So I can now compare exponents. Let's do something pretty strange. Now I can compare exponents. So x equals 3. This one. 2 to the x equals 9. Got it? Okay. So I can't use common bases with this one. So now I have something else I can use. I can use the inverse of exponents, which is logarithm. Okay. So I'm going to say, I'm going to apply a log to both sides. Can I put a log on one side as long as I put it on the other? Yes, I can. Can I multiply it by a strawberry as long as I multiply the other side by a strawberry? Yeah, I can do pretty much anything I want as long as I do it to the other side, right? Okay, so I'm going to put a log on both sides. So I have log to the 2x equals log to the 9. this out. There's actually a proof for it. I'm not going to show you the proof. Miss Wiz would take the time to do all of this. It's nice and pretty, and she's got the proof here. But for our purposes, I don't think I'm going to go and show it to you if you're interested in looking at it. It takes a second to look at it and figure it out. But this is what I'd like to show you right here. Okay, check this out. What do we say logarithms are? Exponents. Do you guys remember this property? A power to a power. So when I have an exponent, and I take it to the power, or to an exponent of it, that's what I'm doing with this, right? I'm taking an exponent, and I'm raising it to a power. Correct? Well, what happens with those exponents when I take an exponent to another power? I multiply them. Well, that's what we can do with logarithms. They have the same properties. Because exponents are logarithms. So wouldn't logarithms have the same properties as exponents? So, log b to the x, this whole thing right here, this is a logarithm. I'm sorry, an exponent. This whole thing's an exponent. What's happening to this exponent? What's happening to this whole exponent right here? What's happening here? It's being raised to a power. Isn't this an exponent being raised to a power? What do we do with exponents that are raised to powers? We multiply them. So technically, I could say, hey, I don't want him raised to the power. He's supposed to be being multiplied, because exponents, when they're raised to powers, are really being multiplied by exponents. So I can take him and put him out front and say, hey, it's an exponent being multiplied by an exponent.
What would you think the power is now?
Hold on. It is. This is an exponent, right? Isn't this exponent right here being raised to a power? So doesn't that mean I can say that they are being multiplied? The exponents are being multiplied? Hold on. Yes, you can, right? So exponents, when they're raised to power, can be multiplied. This is an exponent. Don't look at it as log dx. Log dx is an exponent. It's an exponent being raised to a power. So can't I multiply the exponent times the power? Just like I did there, the exponent times the power. So that's what I did here. The exponent times the power times the exponent. Okay? So whenever you see a log raised to a power, you can say that power is really being multiplied. Here's the way this says it. The logarithm of power is the same as multiplying the logarithm and the exponent. So I'm saying if logarithms are exponents, and I raise an exponent to a power, it's really multiplying it to a power. You can do the reverse too. If ever you have a number out here and you multiply it by a logarithm, you can actually put it as a power. So you can do those back and forth. Okay, so that being said, let's go back to this problem right here. So isn't this a power to a power? An exponent to an exponent? So don't you just multiply them? So now I have x times log 2 equals log 9. Well, how do I get x all by itself? Divided by log 2. Back to the way, and I just got x. Alright, so now I just have x is equal to log 9 over log 2. If I put that in a calculator, which is what we're going to do now, I'm going to approximate it to 3 decimal places. And somebody in the last class said, so Mrs. Roller, why can't I just do this? Here's the log. For the same reason that I can't do this. Can I just do this?
It's 1
It's one number. But some people can look at it and go, they look at it like if it was a variable, you could get rid of it, right? But it's not. It's its own thing. Like this is a number. Log 9 is a number. Log 2 is a number. Specifically, it's an exponent, right? Right? Are we solving for exponents? I'm taking this exponent, dividing it by that exponent, and I get this exponent, which is exactly what I had. I needed an exponent, right? So logarithms are exponents. Okay, so we can't do this, therefore we can't just cancel those logs. So everybody practice right now and put in your calculator log 9 divided by log 2, and let's see if we get the same answer. Log 9 in parentheses divided by log 2 in parentheses. 3.169. I only want 3 decimal places, but this is a 9. So that means this is 0 and this is 7? Yep. 3.17. You can put the 0 behind it. It's the smaller. The 0, I did it with 3 decimal places. It's almost that. Yeah, sure. 3.1714, right? All right, how are we doing so far? Good. Awesome. All right, so there's your proof. You want to go back, wake up late at night, don't have anything else to do? All right, so similarly, natural log e to the n, I can also there's another property in here. Isn't ln, you might as well take the time to guess, isn't ln really log e to the e? Like e. I'm going to say that's just n. Why would I say that? The e's cancel out, right? Because look, if I take this blue part and I just think about it, guys, what is, here's a simple problem, log e to the e. E to the what makes e? Right? Doesn't e to the 1 equal e? Yes. So doesn't this right here all mean equal 1? So it depends. Whenever you've got e to the e, it's just the end. Okay, that's, we'll practice that on the Let's do some more examples. Here we go. So if I had log 2 to the 5, sorry, log 2 to the 2 to the 5th, what does that equal? 5. This is why. Isn't logarithm to an exponent? Doesn't that mean I could pull this out here and put it up front? So this is 5 times log 2 is 2 equals 5. At this point, I can divide both sides by 5 if I wanted to, right? And then I have, this is kind of like a proof, log 2 to the 2 equals 1. Well, doesn't 2 to the 1 equal 2? So this originally, I don't even have to do all of that work if I recognize that 2 to the 2 is 1. All right, let's move on. So, this is my favorite. 2 logs or not 2 logs? That is the question. And we're going to use it over and over again. 2 logs or not 2 logs? That is the question. So I ask you. I will have decisions. 2 logs or not 2 logs? I shall not log. I shall not log. This is what? Can't I find a common base on this? Isn't 25 just 5 squared? And isn't that a lot easier? X minus 3 equals 2. So x equals minus 3 is 2. Is 5 squared 25? Yeah. Yes. I'm going to talk to you like this. Okay. Too long or not too long? Too long or not too long? Too long or not too long? No, not so long.
Nope.
No.
The class is not multiple.
Let's see log. Log 55 to the x equals log 52. Right? Thou shalt log. What's the base of this log? There's nothing there, so what's the base of it? 10. There's no base. Okay, so what shall I do with this log now? Thou shall multiply x. 5 log, because exponent to exponent is multiplication, right? So this comes out front. Alrighty, now what do I do? Now I divide. I'm having too much fun. Okay, so you go away. And then left with x equals log 52 over log 5. Put in the calculator. 2.4 what? 5, what's left with this number? 0, so we're good? Thumbs up, thumbs down. Thumbs sideways. Straight up. That would be a thumbs down, right? Okay. Ready? Moving on. Too long or not too long? I'm going to take it a while. Not too good. Okay. Meter. Meter.
Oh, because there's a thing in the thing.
There's a thing in the thing. We can't do something.
Oh, because
we can't do something to both sides. Logarithms and exponents are all multiplication, right? We can't do all this multiplication until we get that plus 1 out there. So let's get the plus 1 out of there. Right, subtracting 1 from both sides. So really, now we have 2 times 5x minus 1 equals 16. Now, log or not log? No, logging. Why would we log? I don't know. I can have a common base. So I log. Now, here's a question for you. Would I log? Yeah. I log. Here's like 2 to the what? 4. Why would I log? And hurt myself. Okay. So now I have 5x minus 1 equals 4. 5x equals 5. And I can actually check this one. 1. 5 times 1 is 5. Minus 1 is 4. 2 to the 4th is 16. Plus 1 is 17. Did we get it right? Yeah. The beauty of math is check your work. Okay. Too long or not too long?
don't do it.
So, log 2 to the x squared minus 3 equals log 15. Can I do it? Can I go straight here? I'm going to put this out in front, and when I do, it's going to become, I'm going to put this out in front and divide the log. Can I do that at the same time? Are we okay? So I would have x squared minus 3, that's where this fell down here, right? But then I divided both sides by log 2. So So I get log 15 over log 2. Now what? Now what?
Just divide.
If I look at the exact answer, I'm just going to leave it like that. Add 3 to both sides. Now I've got x squared plus x squared equals log 16, that's better, right? Over log 2. Add 3. Now what? If I don't want to square, what do I do to it? Square both sides. The square root of log 16 divided by log 2. This is my challenge. This is a calculator challenge. Can you use a calculator and get as accurate as I can? Alright. I'm going to put it on. I'm going to do it with you guys. Okay? Let's put it on my calculator. So I'm going to pause the recording for 1 second, and then I'll do my calculator, and then I'm going to show you what's in the calculator. Okay, so the answer we came up with our calculator is this. I'm going to go ahead and write in the calculator, and write exactly what I did on the calculator. Okay, so here's my calculator. I hit square root. Then it had to open parentheses for me automatically. Eventually, I'm going to close that. Then I put in, okay, I want division home, so I put in another parenthesis. I put log, it gave me a parenthesis. I put the 15, I closed it. Divided by log, it gave me a parenthesis. I put in a 2 and I closed it. I'm done with division, so I close it. And then I'm going to add 3 and then close it. Okay? Check it. Next one. Just checking. Moving on. Are we good? Alright, see? How about I start this one? Log or not to log? Log. How could we check? How could I check? What would I do first before I decide? I would multiply both sides by 2 over 1. When I do that, this fraction goes away, and I'm left with 4 to the x equals, what's 128 if I take a 2 out of it? Yeah, log or not log? Not log. Yeah. Do you see 4s in there?
Yeah.
We only want 3, right? There are 3 4s in there. So 4 to the x equals 1 over 4 cubed. What else could you do? 4 to the x equals 4 to the negative 3. It's a done deal. Right? Why would I log when I can look at it that simply? There's your answer right there. X equals negative 3.
Oh.
Whenever you do a log and you get a whole answer, you're going to go, oh man, I could just use exponents for this one. I didn't use the log. You should try it. Okay, what about this one? Log or not log?
I wouldn't.
You would have to log it.
Why would you look?
Can you find common basis?
Oh, no.
No, so then we log. If you can find common basis, you make common basis. If you can't, you log. Alright. Let's see. What about this one? Log, loop, or not to loop? We have a common base. Why would you commit when you've got a common base? Fill in. So it's x plus 8 equals 3x. does x equal? All right, let's check. 8 plus 4 is 12. 3 times 4 is 12. Do they match? What's this one? Yes, you do. Let's check. Make sure. So I've got 3 e to the x equals, subtract 1 from both sides, I get 4. Right? Divide both sides by 3. And I get e to the x equals 4/3. Now if I take the natural log of both sides, or min, what do you notice here? Right here. These sound like each other. This is a little imaginary here, right? Anything when these match, this is equal 1. So I have x equals the natural log of 4/3, and you just put that in a calculator. Can you do that for me? Natural log of 4/3. 0.287. Okay, we're almost done. What's the difference between these two? Right here?
What's provided and what has the underneath the number?
Okay, so I heard plus and minuses. When do we use plus? If something's going up in value, when do we use minuses? When something's going down in value, when do we use n? Carrie, had your hand up. When do we use the n? When you've got quarterly, semi-annual, and you're compounding something, right? When do we not use n at all? When it's continuous. All right, got it? So let's go back to the problems we did on that worksheet. So you guys got this. It says Tony purchased and got a signed baseball in the year 2000 for $3. So that's where the 3 comes from. That's where that comes from. Experts estimated that its value will increase by 10%. Increase 1 plus 10% is 1.10, right? And he is 10 years. Intelligent models like this, which is what we use, where A is the initial value of the item and R represents the rate of increase. Do you guys recognize the problem? Yeah. Okay. So it says, use a graph to find the number of years it will take for the value of the baseball to be $20. I started with 3. I want to know what's going to be when it's 20. Or what if it's 20? That's a P when it equals 20. So instead of f of p, right, I want to know after how many years it's going to equal 20. Oh, looky here. Now, when we did it in decimals, right, we went up to the 20 up here, and we went across, and we estimated how many years that would be down here. So it was something like, what? You guys see it from here? 15. What do you think it's going to be? This is 20. What do you think it's going to be? Estimating. How many years? 118. That's reasonable. 18 years? Okay, let's do a logarithm. Alright, so it says use the trace feature. We're not going to use the trace feature. We're going to use logarithm. Alright, so how do I solve this using a log? Is this too log or not too log? Too log. Too log. What am I going to do before I log it? Multiply. You came with a calculator, and that's what we're going to use. 20 divided by 3 equals 1.10t. Now what do I do? What do I do now? I can't find a common basis, so what do I do? Log both sides. So I'm going to put a log and a log. So this is 20 divided by 3, and this is 1.10 to the t. Now what? Yeah, the t is going to come out front, right? The t, because this is exponent to an exponent, right? So exponent to exponent means we can multiply. So now that it's multiplied, now what can I do? Solve. Yeah, I don't know that. What if I use a different multiplication?
No, please. Please, no, please. Not that big.
So I'm going to divide x by 5. Log 1.0. Log 1.0. Put the calculator. Tell me what you get. So I should get 50 is equal to, or about. Is that reasonable? Actually, you get 19.901. Hey, guess what? In 20, it's going to take 19.901 years. Is anybody ever going to say that? You're never going to. You'd say about 20 years, or if I asked you for these one decimal place, you'd say 19 years. Almost. I would say that. Almost 20 years. Okay, how are we doing? We're going to. It's hard. It's not hard to see some of those, right? Is it really that complicated where you go, oh my gosh, it's mind-blowing? No! All you ask yourself is what? What do you think you ask yourself? Log or not to log? When do you log? When I can find a common base, I don't make the log. Here's another one. The value of the truck purchased new is 28 grand. Decreasing by 9.5. There's that decreasing. It went down by 9.5. 1 minus 9.5 is 0.905. Because 9.5 is actually 0.095. Write an exponential function, situation, and graph it using a calculator. Use the graph to predict after how many years the value will drop to 5,000. Where would I put 5,000? Where would I put the 5,000?
Oh, yeah, there's no
equal sign. So I want to know, when this all happens, when is this price going to drop to 5,000? So in all of these guys, you're going to log, right? And you're going to use your calculator. So I'm going to divide both sides with 28,000, take the log of both sides, divide by log 0.905. One more time? Yeah.